It's funny. We flip switches, we charge our phones, our entire lives basically run on it. But if someone asked you what electricity actually is, could you tell them? It's this invisible, almost magical force we use every single second. Well, today, we're going to pull back the curtain on that magic. All right, let's get right to it. What really is this stuff that runs our modern world? Now, don't worry, we're not going to get bogged down in complex physics. To really get a handle on electricity, all you need is one simple, really powerful idea. And here it is. I want you to think of electricity as water flowing through a system of pipes. Seriously, that's it. If you can picture water moving through a pipe, you are already halfway there. This simple idea is the key to understanding everything else we're going to talk about, so keep it in your head as we move on. Okay, so to really understand this flow, we need to wrap our heads around three core concepts. These are what I like to call electricity's big three: charge, current, and voltage. They are the absolute fundamentals. Let's break them down one by one. So first up, we've got charge. The easiest way to think about charge is that it's the actual stuff that's moving. It's the physical substance, a fundamental property of matter that's carried by these teeny tiny particles. You've probably heard of them, electrons. So let's bring it back to our analogy. If charge is the stuff, then in our pipe system, what is it? It's the water. Simple as that. Charge is the water itself, just sitting in the pipe, ready to move. Okay, so if charge is the water, then what's current? Well, current is the flow of that water. It's the movement. It's basically a measurement of how much of that stuff, how much charge, is passing a single point in, say, 1 second. Right, so think about a gentle little stream that has a low current, but a big rushing river that has a super high current. It's all about how fast and how much water is actually moving through that pipe. But that brings up a good question, right? What makes the charge, move in the first place? It doesn't just flow on its own. And that, my friends, is where voltage comes in. Voltage is the push. It's the pressure. It's the force that gets everything moving. Your car battery, for example, that's what provides the voltage, the push, to get the charge flowing. And in our pipe analogy, this is just the water pressure. You can imagine a big water tower pushing down, creating a lot of pressure, or maybe a really steep hill that makes the water flow super fast. The key takeaway here is simple: no pressure, no flow. And in our world, no voltage, no current. They go hand in hand. All right, so now we know that current is the flow of charge. But it turns out that flow can happen in two very different ways. So let's take a look at the two distinct types of current that power, well, pretty much everything in our world. First, you've got direct current, or DC. This is the kind of power you get from batteries. Think of it as a nice, steady, one-way river. It just flows in one direction, which is perfect for sensitive electronics like your phone or your laptop. Then you have alternating current, or AC. This is the stuff that comes out of the sockets in your wall. And it's totally different. The flow literally goes back and forth, constantly changing direction. Now, why would we do that? Well, it turns out AC is way, way better for sending power over really long distances, like from a power plant all the way to your house, without losing a bunch of energy along the way. Okay, so we've got our water, the charge, we've got our flow, the current, and we've got our pressure, the voltage. But where does all this happen? Well, it happens inside something called a circuit. And you can think of circuits as the highways and roads for electricity. Now, the number one rule of circuits is that they have to be a complete closed loop. No gaps allowed. Here's another little analogy for you. Imagine a long tube that's completely packed with marbles. If you push a new marble in one end, one instantly pops out the other, right? But what happens if there's a break in that tube? You can push all day, but nothing's going to come out the other end. Electricity is exactly the same. The second you open a switch, you create a gap. The path is broken, and the flow just stops. Everywhere. Instantly. And these electrical roadways can be designed in two basic ways, either in series or in parallel. And trust me, how you hook things up makes a huge difference in how the circuit works, especially with things like voltage and what happens when one little part of it fails. First, let's talk about a series circuit. This is where everything is wired up in one single continuous line, one thing after another. That means the current only has one path to follow. But here's the catch. All the components have to share the voltage. And even worse, remember those old Christmas lights where if one single bulb burned out, the entire string went dead? Yep, that's a series circuit. One break in the chain and the whole thing is kaput. And that is exactly why your house is wired in parallel. In a parallel circuit, every light, every outlet, every appliance gets its own separate branch, its own little path back to the power source. And this is a game changer. It means every single thing you plug in gets the full, proper voltage. And it means if your toaster decides to give up the ghost, your TV and your lights keep on working just fine. Each path is totally independent of the others. Now, having all this power flowing invisibly through our walls is obviously super useful, but let's be real, it can also be pretty dangerous if it's not handled correctly. So for our last section, let's talk about some of the really clever safety features that are built right into your home's wiring to make sure everything stays safe. Okay, so if you were to ever open up a standard plug, you'd find 3 wires inside. The brown one, that's the live wire. It's the one carrying all the high voltage, so yeah, that's the dangerous one you don't want to touch. The blue wire is the neutral wire, and its job is to complete the circuit. And then you've got that green and yellow striped one. That's the earth wire. And it's a super important safety feature, as we're about to see. So what happens if something goes wrong and you get a sudden power surge? Well, that's what fuses and circuit breakers are for. They both do the same basic job: protect your stuff from getting fried. A fuse is really simple. It's just a thin piece of wire that's designed to literally melt and break the circuit if the current gets too high. It's a one-time-use deal. A circuit breaker, on the other hand, is like a resettable fuse. It's an automatic switch that just trips when there's a surge, cutting the power. And all you have to do is go to your fuse box and flip it back on. But then, you've probably noticed that some things, like your phone charger or maybe a hairdryer, only have 2 prongs on the plug. So where's the earth pin? Well, those devices are what we call double insulated. It means that on top of the normal plastic coating around the wires, the entire outer casing of the appliance is also made of an insulating material, usually plastic. With that extra layer of protection, there's basically no way the outside of it could ever become electrically live, so it just doesn't need an earth wire. So there you have it, from the pressure of voltage to the flow of current, all the way through the pipes of a circuit. Electricity isn't quite so mysterious after all, is it? When you boil it all down, it's really just this invisible river of energy that we've learned how to manage and control. So the next time you flip a light switch, maybe for just a second, you'll actually see it, that invisible river flowing right there inside your walls.